In Europe, some of the glucose from crops is fermented to produce ethanol. So let's have a think about what that glucose we know is C6H12O6 and ethanol C2H5OH. Use of a carbon neutral fuel leads to no net emissions of CO2 to the atmosphere. The ethanol produced by fermentation of glucose may be regarded as carbon neutral. Justify this statement, including the relevant chemical equations in your answer. So I think the first thing we need to do is realise that where does glucose lock in carbon dioxide from the environment? Well, it does that during photosynthesis, where carbon dioxide and water combine to make the glucose and the oxygen. And if we balance that equation, we can see that we're locking in 6 carbon dioxides from the atmosphere. We then take that glucose that we've just created and we ferment it with yeast to form ethanol, and it produces carbon dioxide. And if we look at balancing that equation, we can see that we get that. So at the moment we've minus 6 CO2 and then we've plus 2 back into the atmosphere. If we then take those 2 ethanols that we've produced in fermentation and we combust them as a fuel, then we will see we'd get 4 carbon dioxides and 6 waters. If we balance the oxygens in that equation, we can see that we need 6 oxygens. And so we've added another 4 carbon dioxides into the atmosphere. So we can see from our bracketed numbers that we took out 6 from the atmosphere, but we put back in 6. So ethanol produced in this way removes 6 CO2 from the atmosphere but fermentation and combustion add in total 6 CO2. Hence, it can be considered carbon neutral. Coffee beans from South America are exported to Europe in an outer layer called silver skin. The waste silver skin can be fermented to produce a solution containing propanone, C3H6O, ethanol, C2H5OH, and butanol, C4H9OH. Suggests why ethanol produced in Europe using silver skin from South America is less likely to be carbon neutral than ethanol produced from crops grown in Europe. Well, if we have to get that silver skin over from South America, the transport will have carbon emissions. So the transport from South America will release CO2. We've got carbon emissions. Table 2 shows the enthalpy of combustions of 3 fuels from the fermentation of silver skin. One way to measure a fuel's environmental impact is to measure the amount of energy released per mole of CO2 produced. Complete Table 2. Use your answers to deduce the fuel with the lowest environmental impact by this measure. So if ethanol has 2 C's, then to figure out the value for ethanol, it would be split between 2 carbon dioxides. So it would be, and this says released here, so we don't need the minus sign anymore. It would be half of 1,371, which is 600 at 85.5. If we take butan-1-ol, which has got 4 Cs, and we divide 2673 by 4, because it would make 4 CO2s, we get 668.25. And if we take propanone, which has got 3 Cs, so if we divide 1786 by 3, we get 595.3 recurring. It says, use your answer to deduce the fuel with the lowest environmental impact. So we want the one that releases the most energy per mole of CO2, so the one with the highest value, which would in this case be ethanol. So the most energy per mole of CO2. A student investigated the combustion of propanone using calorimetry. A copper calorimeter containing water was heated by the complete combustion of some propanone. The student did not record the final temperature of the water. Table 3 shows the results. Use Table 3 to calculate a final value for the temperature of the water. Assume no heat was lost and that the heat capacity of the calorimeter is negligible, and that the enthalpy change, our delta H, is minus 1,786 kilojoules per mole, and for water the specific heat capacity is 4.18. So I think the first thing to do would be to find out how many moles of propanone that we burnt. So we did 1.18 grams, and we need to add up the MR of propanone. So we add up C3H6O. We find out that we burnt 0.0203 moles. So if we want to find the heat released by that propanone, we're going to take the 1,786 kilojoules per mole and times it by our 0.0203 moles. That's how many moles we had. And we're going to see that we released 36.3 kilojoules. Now, what we would need to do is remember that when we're using the specific heat capacity, this is in joules. So we're going to convert our number to joules by multiplying by 1,000. So 36336 joules. So our heat released is equal to the mass of the water times specific heat capacity times the temperature rise. We go back up and look at how much water, 260 grams. We're going to find out our delta T. So we can rearrange that to find our delta T. And we get a delta T of 33.4 degrees C. Now, given that the temperature started at 22.3, the final would be 22.3 add the 33.4, because it's an exothermic reaction, the temperature needs to go up. And so we're getting 55.7 degrees C. Butan-1-ol can be added to petrol for cars. An equation for the complete combustion of butan-1-ol is shown. Table 4 shows some mean bond enthalpies. Use the data to calculate the value for the mean bond enthalpy. C bond, I'm going to add it to the table and call it X. So we've got the value here. So minus 2,504 equals the sum of the bonds broken minus the sum of the bonds made. Now, if you struggle to identify them, it may be worth just sketching out. I'm just going to do sticks for the hydrogens, but I can then see the bonds. I've got 6 O double bond O's. I've got 4 CO2s and 5 H2Os. So minus 2,504 is the sum of the bonds broken. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 4 1 2s. We've got 1, 2, 3 of the bond we're trying to find, the CC bond. We've got a 360 and a 463. Oops. And then we need to add on to that the 6 OO double bonds. And then we're going to subtract from that the bonds that we've had to make. So we're going to subtract from that 8 805s and 10 463s. So this is where we need to use our calculator to add up these values. So if we add up everything in the left bracket except the 3x, we get 7507. We've still got the 3x. If we add up the right hand bracket, we get 11,070. So then we can work out that 3x equals minus 2504 minus 7507 plus 11070. So put that on your calculator. And you get that 3x equals 1059. And so then if you divide that by 3, you get 353 for the value of a CC bond. And then butan-1-ol can be manufactured by reacting steam with but-1-ene in the presence of the catalyst concentrated sulfuric acid. In the first part of this process, but-1-ene reacts with concentrated sulfuric acid to form W and X. But-1-ol is then made from W. Name and outline the process for the conversion of but-1-ene into W in the first place. So this is a reaction of an alkene. This will be an electrophilic addition. So we need to start with but-1-ene. So if we imagine drawing out our double bond, and this is carbon number 1, then we've got carbon numbers 2, 3 and 4 on one of these branches. So carbon number 1, 2, 3, 4. I'm just going to remove those little numbers. And then what we're going to do is we're going to use sulfuric acid. So remember that we need to draw that out, that HO bond in sulfuric acid is then joined to the S. And we can see that they've drawn it out for us. I'm going to abbreviate it slightly to avoid having to draw so much. And then the alkene double bond is going to attack the delta plus hydrogen and break the bond between the hydrogen and oxygen. That's going to lead to our carbocation intermediate. So we're just going to open up that double bond. Actually, I'm going to rewrite that. I'm going to actually put it on this stick just to make it tidier. Move the hydrogen to here. Now, given that we want to form W at this point, we need to put the hydrogen on the left-hand carbon and the positive charge, the carbocation, on carbon number 1 because we're trying to form compound W. Now, this is the minor product, so we do just need to bear that in mind, that we're actually not drawing the product that we would normally think to draw. And this is giving us compound W. There is a very low yield of butan-1-ol from but-1-ene in this manufacturing. Explain why. So, as I said here, we made a primary carbocation, which would be the minor, the less stable carbocation, leading to the minor product. Oops. So we'll just go butan-1-ol is the minor product formed via the less stable primary carbocation intermediate rather than the secondary carbocation intermediate.